Hi everyone, and welcome to our last week of lecture for this course. This week we're going to discuss assessing body composition. And I want to ensure that when we think of body composition, we're not thinking solely of percent body fat, but we're also considering all of the components of your body. So this includes soft tissue, as well as lean mass, as well as bone, and as well as fat content. And essentially, it's more than just percent body fat. We're going to consider girths and segmental changes in size, which are extremely important. So the first thing we need to do is, again, go back to our needs analysis. Is tracking changes in body composition a useful tool for your client? So some examples of where it would be useful is for individuals who would like to lose weight and change their body composition, as well as for individuals who are competing in weight-dependent sports, also for tracking health status, helping in the periodization of nutrition as well as body composition, as well as finding the optimal body composition for performance. Now, everyone has a different ideal body composition for performance to make the person more resilient to injuries and sickness. So these are all important factors that need to be considered and asked when doing your needs analysis. The plan for today's lecture is sixfold. Firstly, we're going to discuss the reasons for assessing body composition. Then we're going to move into discussing the direct and indirect methods, then the multi-compartment model. Then I'm going to present 4 indirect methods of assessment, which are the most common. Then I'm going to talk about a comparison study that I did about 5 years ago at the Canadian Sport Institute. And then lastly, we're going to talk about protocol standardizations to ensure that we have valid and reliable data. Let's begin by discussing some of the rationale for assessing body composition. The first reason is to monitor the success of your training, your exercise prescription, or a nutritional intervention. So you're assessing changes, segmental changes, as a result of training. So are your quads getting more lean? Are you changing the body composition, the bone densitometry of the area that you're working? So depending on the needs and gap analysis for your client, you can use assessing body composition as a means to gauge their training adaptation. As well, if you put an individual on a specific nutritional intervention, you can monitor the changes in girths, changes in bone and soft tissue, and look at the impact of that nutritional intervention on body composition changes. Okay, so an example of this is in wrestling. So wrestling and weight cutting sports. So are you actually, when you cut weight right before a major event, are you actually losing lean mass or fat-free mass? Or are you losing fat mass? And that's an ongoing question. So this may change certain strategies because if you are losing a lot of muscle mass, then you may choose a different method. You may choose hyperhydration instead, or different strategies to try to prevent the loss in lean body mass. And you could do this through assessing body composition. The second way or reason for assessing body composition is to monitor the health status of your client. As we know, abdominal fat is correlated to an increased risk of cardiovascular disease. So you can monitor the health status of your client over time by looking at girths and segmental changes in body composition and providing this feedback back to your client. The third reason for assessing body composition is to determine the optimal body composition for best performance, training resiliency, and injury prevention. Now, this is huge because the way that you eat and the changes in your body composition will dictate how quick you are to recover, whether you're performing the best, and whether you're more prone or resilient to injuries. A prime example of this is Claire Hughes, who you can see cycling in the background here. She's the most decorated female athlete in Canada, both in summer and winter Olympic sports. And when I was her roommate at multiple different cycling events because we were in the national team together, and she would always say, "Heather, I'm the heaviest girl in the cycling peloton. However, if I lose 1 pound or 1 kilogram of weight, I lose my power. And my power makes me the best cyclist I can be." So she already knew that if she got too lean and lost muscle, she actually would hinder her performance. So yes, she was the heaviest girl in the peloton, but she could outclimb on a mountain any girl in the peloton and still win. So she was highly successful, and so she knew exactly what body composition she needed in order to produce the most power and be the most resilient to injury and be the most adaptive to her training plan. So that's a prime example. Every athlete has a different body composition for which they will perform the best. When I was too light and cycled too much and didn't eat enough and I lost too much weight, I got sick more frequently and I didn't recover from injuries as well. And I didn't respond as well to training. So all of these are important. These are very important factors that you need to consider when you're working with athletes, is finding their optimal body composition to have optimal performance, training resiliency, and injury prevention. The last reason to assess body composition that we're going to discuss in this lecture is that body composition is related to health complications. So, for example, disordered eating, where you can have both spectrums. So, disordered eating can be defined as eating too much food or eating too little food for energy output, that there's a disbalance between energy in and energy out. Okay, so disordered eating can be both spectrums, either eating too much for what you're doing or eating too little for what you're doing. That affects your body composition and health-related outcomes. Second of all is athletes can have stress fractures, and this can be linked to relative energy deficit syndrome, or REDS, also known formally as female athlete triad, where there's this link between bone health, energy output, and disordered eating. So these are all linked. And we've moved away from the female athlete triad to talk about REDS, and this is the relative energy deficit syndrome, because this not only affects females, it also affects males. And when your body composition changes in a not a great way, you can lead to hormone imbalances where you have suppressed testosterone for males and not be non-responsive to training. You can also see menstrual dysfunction in females where you lose your menstrual period. And this can lead to stress fractures and an increased risk of injury. So tracking body composition over time for an athlete can be extremely important to track their health. That ultimately, if there is disordered eating or an eating disorder, it can lead to stress fractures. It can lead to hormone imbalances, which prevents the athlete from adapting and doing well with training and performance. So ultimately, monitoring body composition changes can be a great tool to gauge the success of training prescription, to monitor the health status of your client, determine what that optimal body composition is to reduce the risk of injuries, to have training resiliency, and to have good performance. Ultimately, it's about the health and well-being of your client. And if body composition assessments is a good method and tool for which you can do this, then I would integrate it in. A few more comments about why we assess body composition. First of all, the focus should be on fat-free mass. Okay, so fat-free mass is anything that's not fat. And it's frequently used to standardize or index physiological variables such as resting metabolic rate and power. So a common unit to now use is for cycling is watts per kilogram of fat-free mass. So now we're isolating how much muscle mass the individual is, and we make nutritional interventions based on their lean body mass. So we're looking at fat-free mass now. As well as training methods have become more sophisticated, each athletic group has become more specialized. So now we're modifying its typical physique imperatives away from general morphological norms. And what I mean from that is you can look at these two athletes in the picture. The top one is Ryan Lochte, and the bottom one is Ryan Phelps. They're both highly successful swimmers for the United States at the previous Olympics, multi-decorated swimmers. But if you look at them both in person, one is over 6 foot tall and very long levers, very lean, the stereotypical good swimmer. or good swimming physique. Meanwhile, Ryan Lochte is shorter. He's 5'8". He's huskier. He's a thicker build, and he's completely different than Ryan Phelps. However, Ryan Lochte is a very successful swimmer as well. So we're moving away from this idealism of the ideal physique for a specific sport. And both of these are phenomenal athletes, but very different phenotypes. So again, we're moving away from phenotypic classifications. Instead, we have large individual variability, and it's finding what the ideal body composition is for each athlete. Another example of this is when I was younger, I was very tall and lean. And so as a child, I was told by gymnastics coaches to my parents, don't put her in gymnastics because she's tall and lean and we need short and more power-based individuals for gymnastics. So this was like in the 80s and 90s. And now we're moving away from this, right? Because it really comes down to how well you can move in your skin and how well and coordinated you are with the body you have. So we're moving away from these phenotypic classifications, that there's large individual variability, and you don't want to limit someone based on their phenotype. You want to work with their phenotype to determine the ideal body composition for them to perform the best. Ideally, you want to partner a body composition assessment with some sort of performance measurement to try to find the ideal body composition for a performance. So whenever I do a body composition assessment of my client, I also do some sort of performance assessment. Okay, so I'm assessing their physical characteristics, their physiological characteristics. So then I see, okay, your test results are really, really good, and your body composition is like this. So we're trying to figure out what that ideal body composition is for that athlete. Now let's begin to talk about direct versus indirect methods of body composition. There's no real gold standard for body composition with accuracy that's less than 1%. So a direct method of body composition is not an option because that requires dissection of the body, and nobody would volunteer for this while they're still living. Okay, so a direct method is not an option when it comes down to body composition, unless it's post-mortem. All right, there are, however, several different indirect techniques, but they are not all created equally. You want to pick the best indirect technique that's representative of your population and your demographic. The choice of body composition technique often depends on the intended purpose for which the data is to be used, as well as the available technology. So if you do not have any technology, but you do have skin calipers, then you would use surface anthropometry. But if you have technology, then you can combine surface anthropometry with the tech that you have to get a better indication of the individual's body composition. So the closest researchers can get to a direct method of body composition, as far as accuracy goes, is by using the multi-compartment model, also known as the 4C technique. It's called the 4C because you're splitting the body into 4 components. You're splitting, and we'll talk about this on the forthcoming slide. This is considered the best reference technique, but I want you to be mindful of this. It's called the 4C, 4-compartment technique. So you're splitting your body into 4 compartments only, which really simplifies the body because, as we know, we are extremely complex and we've been designed with multi-compartments, multi-different types of tissue. But this method, although it's considered the best laboratory reference method or the best reference technique, is still limited. Now let's discuss the indirect assessments, which you're more familiar with. This is where we have a surrogate parameter is used to estimate tissue or molecular composition. For example, determining what body density is. And then once you have body density, then you're putting the body density into a linear regression equation to determine the percent body fat or the body composition parameter that you're trying to assess. So this then leads to something called a doubly indirect, where one indirect measure is used to predict another indirect measure. So if we have ascertained body density, okay, by using one of these techniques in the picture, then we put body density into a regression equation. So this would be a doubly indirect. Okay, so regression equations are considered doubly indirect because you're getting a surrogate parameter and then you're putting that surrogate parameter into an indirect measure or a regression equation. So the use of regression equations also means that these approaches are sample specific, that you want to pick the best linear or regression equation for your population. So for example, the BOD pod, which is at the top, it looks like that little spaceship, provides one output, and this is body density. Then the machine actually takes the body density and puts it into one of 3 or 4 regression equations that are inherent to that machine. So the BOD pod system does that. So it determines, first of all, your body density, then it puts it into one of its pre-established regression equations based on the demographic information that you put in for your client. And then it spits out your percent body fat and your percent lean mass. So this would be a doubly indirect method. We also have bioelectrical impedance, which is up on the right-hand corner. We have your surface anthropometry, where you're taking a skin fold, you're taking the thickness of that skin fold in millimeters, and you're putting it into a regression equation. So that is called the doubly indirect method. You get the sum of that girth, and then you're putting it into a regression equation. We also have DEXA, which determines different factors, and it uses regression equations as well. So all of these, which we're going to talk about more on the forthcoming slides, are indirect assessments where we find a surrogate parameter, such as body density, such as another factor, and then we're using a regression equation. Here's a figure outlining the different types of indirect methods. So on the left-hand side, we see absolute body mass. And we see the first column being a 2C model, so 2-compartment model. And the example here is underwater weighing or hydrostatic weighing. You may have heard of this before. So what this method does is it splits your body into 2 compartments only. So it doesn't consider bone, it doesn't consider other types of tissue. It basically splits your body into fat or fat-free mass. So everything that's not fat or adipose tissue is under fat-free mass. So this would be your muscle mass, this would be your bone, this would be your cartilage, this would be your ligaments and your tendons. All of this would be fat-free mass. So it's very crude in the sense that this method, underwater weighing, splits your body into 2 compartments. If we move to the middle column, we see the 3-compartment model, and this is known as the DEXA or densitometry. Okay, and this splits it into 3 compartments. So the beauty of the DEXA is it measures your bone densitometry as well. So it splits your body into only 3 compartments now. We have fat, we have lean mass, and we have bone. Okay, so let's think about this for a second. Where does your organ mass lie? Is it classified as fat, bone, or lean mass? Well, it's actually considered lean mass. It's quantified as lean mass. So when you get this information, it's not of your lean mass, it's considering your organs as well as lean mass. So this 3-compartment model is more accurate because it splits your body into 3 compartments instead of 2. However, it's still quite crude. The 4C model, which I said is now the leading reference technique, splits your body into 4 compartments. We have fat, and this is the furthest column on the right. We have fat, we have protein, which would be your lean mass, your muscle mass. We have water content, and we also have bone. And this is called the 4-compartment model. So now we're splitting the body into 4 compartments, which increases the accuracy of the measurement. So as we move from the 2C to the 3C to the 4C, we get a more accurate or valid measurement of what an individual's body composition is. Remember, the 4C model is the leading reference technique because we can't do direct measures. Obviously, we can't assess your entire body composition directly. So what we do is we get the best reference method, which would be the 4C model. And we'll talk about this on the forthcoming slides. So the 2C model would be hydrostatic weighing, it would be the BOD pod, it would be air displacement. All of this is the 2C, which splits your body into 2 compartments. The 3C is only the DEXA method, which we'll talk about. And then the 4C is the leading reference method. And funny enough, measuring total body water content is extremely hard. And we'll talk about that on the next slide. Now let's discuss the multi-compartment model, which is the 4C method, where we're splitting the body into 4 compartments. This is known as the leading reference method for body composition because we have the most compartments that we're splitting the body into. This requires a combination of measurements. So we firstly need to determine body mass of the individual by using a scale, a validated scale. So you want to make sure that it's calibrated and that's a proper scale. The second assessment we need to do, or metric we need, is body density. And this is determined using air displacement, which is the BOD-POD, or underwater weighing, known as hydrostatic weighing. Okay, so you have to do that method. So you have to have access to the BOD-POD to get that measurable. The third piece that we need for this is bone mineral mass, which is only determined by the DEXA, dual X-ray absorptiometry machine. Okay, the DEXA. It's the only machine that can measure bone densitometry. So we have to find out what the individual's bone mineral mass is. The fourth variable that we need is total body water, which is the hardest method to determine. And this is, we use something called deuterium, or 180 labeled water dilution, which is almost a 24-hour assessment where we give an individual a labeled water dilution. They drink it and then they come back within 12 hours and you can monitor where the water is in their body. And that gives us an indication of their total body water. Okay, that's the hardest method, hence the reason why the 4C, this multi-compartment model, is quite hard to do, and you need the proper laboratory or laboratory equipment in order to get this information. So it's not always the preferred method, however, it is the most accurate. Okay, so then once you have these 4 metrics, body mass, body density, bone mineral mass, and total body water, we put in those variables into the equation that's on the slide. So we have percent body fat equals a constant divided by body density minus another constant times your total body water over your body mass plus another constant times your bone mineral mass divided by the body mass minus 179, which is another constant. And this gives you an indication of your percent body fat. So this is the multi-compartment model. It gives you the most accurate method for determining body composition. Now let's talk about some of the pros and cons to the multi-compartment model. First of all, technical errors of estimating body density, body water, and bone mineral mass have been combined to yield a percent body fat error of approximately 1%. So you still have a 1% error. So if you're reporting that the individual has 25% body fat, this could be plus or minus 1%. Okay, this isn't that bad. This is the lowest percent error that you can get out of any technique for body composition. And we'll talk more about this as we continue on. So what are some of the limitations to the multi-compartment model? Well, first of all, it's time consuming. It requires a lot of laboratory and sophisticated technology, which also often places them out of reach for practical application in sport and in health. And you require a qualified technician to run the equipment. So the interpretation of bone densitometry, as well as air displacement, as well as the determination of total body water requires technical expertise. And here's a quote down here. While multi-compartment models require more equipment, time, and tester expertise, they represent the new gold standard for profiling, monitoring change, and serving as a criterion against which field methods can be validated. So it is accurate to approximately 1%. So that's the benefit of it. It's quite accurate. It's the best for monitoring change over time. However, the practicality is very low in that most people don't have access to this sophisticated equipment. So the 4C model, although it's the leading reference method and considered the gold standard for profiling, it's not necessarily attainable for many individuals, including most of us. Now let's discuss the indirect methods of assessment. First of all, the DEXA, also known as the Dual Energy X-ray Absorptiometry machine. This is a picture of the machine. It's a nice scanning bed where the client lies on it. It's very comfortable. And the scan arm takes pictures and segments along your entire body and basically gives you a picture, a skeleton picture, and of your soft tissue as well as your bone mass. You can somewhat see it on the screen of the computer, the little picture of the individual. So this is the pictures that it takes of your soft tissue as well as your bone mass. So it's considered the diagnostic method of choice for osteoporosis, osteopenia, and increased use in the quantification of soft tissue. So I currently am a clinical densitometrist. I use this machine at the Canadian Sport Institute to track changes in body composition of athletes pre and post injury, as well as when they first get registered at the center, to see what their body composition is, and tracking changes in lean mass, segmental lean mass, fat mass, as well as their bone densitometry to ensure they're in a healthy state. So what does it do? Well, it essentially passes filtered X-ray beams, so it is an X-ray machine, at two different photon energies through the participant that are attenuated differentially by the material in their path. So if it's fat mass or lean mass, it will the photon beams will be different through each of the tissue. So the density of the tissue determines how well those photons move through the tissue. So with the participant lying on the scanning table, the process maps the mass and composition of each pixel in terms of bone, mineral content, fat, and fat-free soft tissue. So fat mass is determined by the ratio of soft tissue attenuations at the two energy levels. The only thing with the DEXA has been criticized because it assumes segment constancy in tissue composition. However, as we know, water and lipid content of skin, adipose tissue, muscle, and bone exhibit regional variations. So what does this mean? Well, essentially, we're assuming that the water content is the same throughout the entire body in every single tissue, which we know is not true. That fat or adipose tissue, lean mass or muscle mass, organs, all of this have regional variability in the amount of water content. And so this method assumes constancy throughout the entire body. As well, we're splitting the body into 3 compartments only without considering water content, so that decreases the accuracy of the machine. However, the beauty of this is it's an easy scan, and it's done within 6 minutes, and you get an indication of the bone mass and bone densitometry, the bone health of your client. So now let's look at the advantages to the DEXA. It is a 3-compartment model, so it's better than the 2 compartments. We also consider bone mass. So you can see the report that someone would get over on the right-hand side. So you can have your own personal bone skeleton or Halloween card that you can put up of your own skeleton, which is pretty cool. And then the right picture is your soft tissue. So you can actually see your lungs and your heart tissue as well as abdominal tissue, etc. So it's pretty cool. It's a really cool system, and you get this picture and you can track changes over time. The second advantage of the DEXA is it's very fast. It only takes 6 to 7 minutes or up to 10 minutes if the individual is quite thick. But this is like a little siesta in the afternoon. The person just lies there. It's non-invasive. They can have a little snooze for 6 to 7 minutes. So it's quite convenient. It also is the only machine that does an assessment of bone density. So it provides how thick your bones are, whether you're on track for osteoporosis, osteopenia, all of these factors. As well, it's low radiation dose. So it is an X-ray, so there is a radiation dose, but it's the same amount of radiation that you would get in background radiation living in the city of Toronto per day, or what radiation dose you get from flying to San Francisco and back. So a long-haul flight of radiation. So it's very minimal. However, you only should have around 3 to 4 DEXA scans a year. As well, for individuals who are in childbearing years and women, I always ask them to do a pregnancy test just quickly beforehand, just to ensure that they're not pregnant before they get scanned. The beauty of the report, you can see on the right-hand side, you can't see it very clearly, but what it does is it provides regional composition data. So this means that I can see how much muscle mass is in your right bicep versus your left bicep versus, your left quad and your right quad. So you can look at asymmetries between body parts, as well as asymmetries not only in muscle mass, but also in fat, as well as in bone. Okay, so you can see the impact of an injury. So if you break a bone in your body, you can look at the amount of atrophy that happened both in the bone, but also lean mass and the changes in fat mass. And then you can put the individual on a rehab program, and you can monitor the changes that occur as a result of that training. So you can check to see if bone mass and lean mass have been regained to what it was beforehand. So I always do this test routinely on athletes, usually 3 or 4 times a year, to track changes in their body composition in response to their training, as well as different times of the season and competition, what their body composition is, linked with a performance measure to see what that ideal body composition is for them to perform well, but also be resilient to injury and resistant to more colds. So it's a beautiful tool that can be used well. I am a clinical densitometrist, so I'm trained to be able to use this system, and you can get the certification through the International Society of Clinical Densitometry. So here's a nice picture of a report, so a DEXA analysis printout, which is done and created within 6 minutes after you do your regions of focus. The first thing I want you to focus on is that we move away from the fat mass and we focus on lean body mass changes. So you can see with what's highlighted, you can compare with young groups, you can compare within yourself, you can look at health indices, you can look at changes, segmental changes over time. So if you can zoom in on your PowerPoint slides to look at that report, it's really, really cool. If you ever get a chance to get a DEXA done, I highly recommend it. It's pretty cool, the x-ray images that you get of your soft tissue, but also your bone and your skeleton. It also provides information about your hip to waist ratio, as well as it provides a really good method to track change over time with injuries or with training, just to see, okay, I'm doing all these pull-ups, am I actually changing in my upper body strength? Where are the changes being done? All of these factors. So it's really cool in that regard. Now let's discuss some of the limitations to the DEXA. The scan bed isn't that long, so for individuals who are greater than 192 centimeters, the bed is too short. So any elite basketball player cannot fit on the scan bed. And so you have to do 2 scans. One, you have to do a scan where their head is on the bed and you cut off their feet from the image. And then you have to do the second scan where their feet are on the bed and their head is cut out of the image. And then you're supposed to piece those 2 images together to give an indication of their body. So this is obviously not ideal, and it increases the technical error involved in the interpretation of the results. As well as soft tissue may migrate beyond available width of the scan area. It's relatively narrow, the scan area. The bed is quite narrow. So for individuals who are larger or an athlete who's quite thick, it's really hard to get them fully on the bed. So again, you have to move them over so one half of the body is on the bed and do a second scan where the other half of the body is on the bed. And then you have to piece the results together of those 2 scans, which again increases the error rate, and the interpretation of the results may be a little flawed. As well, there's a max kilogram for the bed of 120 kilograms, which isn't that much. So there are some limitations. There is quite a bit of variance between software and between manufacturers. So there are multiple manufacturers that make DEXA scanners, and there's something of a difference of 5 to 8% variance between these scan beds. So it's ideal that if you get tested, you always go back to that same clinic that has the same bed to minimize the variance. Because if you get tested at one clinic and then 6 months later you get tested at another clinic with a different software as well as a different machine, then it might be off by 5 to 8%. And that's huge because it may be reporting that you're at 25% body fat at one area, and then the next place you go to six months down the road after being on a nutritional intervention and exercise intervention, you could be 8% higher, but this is not indicative of true change. So you have to be, whatever scan bed you're using, you have to consistently use that each time. You also require a qualified technician and with their known error of measurement, which is really important. You can only have a max of 4 scans per year due to the accumulated radiation dose. And the measurements of athletes who are excessively small, large, or lean may induce errors greater than for subjects of standard size and composition. And this is because the system is using regression equations. So it's collecting these three variables: soft tissue, fat mass, fat-free mass, and bone mass. It's putting that information into regression equations. So it's doubly indirect to provide you with the information needed. And so if you're outside where those regression equations were made, the demographic for those regression equations, the results will not be as accurate. So here is a nice optic showcasing some of the sources of error. So remember, every method has sources of error that you want to try to mitigate and decrease. So here are the sources of variability of error associated with the processes of undertaking a DEXA scan to measure body composition. So first of all, we have technical error, which is in brackets with a T. So technical error would be consistency of scans within and between subjects, the demarcation of regional composition, which the individual, the technician, would do afterwards. So there's technical error there. The technician also needs to place the subject or the participant on the bed, which if you position them differently each time, it can increase the source of error. As well, machine has inherent technical noise, which increases technical error. The subject's clothing is a form of technical error. So if at one time you get scanned fully clothed versus the next time you're just in your undergarments, that's going to be different because your clothing has to be quantified as one of the three variables, as bone, as fat-free mass, or fat mass. Okay, so you want to ensure that you're consistent each time in how the person presents themselves, that they wear the same clothing every time. Lastly, the B is biological variation, in brackets, is subject's presentation. This is how they present themselves, how they come to the lab. Are they acute or chronically dehydrated or hydrated? So their hydration status, because we're not measuring total body water, we don't know how hydrated they are or dehydrated. So this provides a way of biological variation because remember, we're not measuring total body water. So therefore, the water content of the individual must be classified as either fat mass, fat-free mass, or bone mass. And so if someone is dehydrated versus being hydrated, it's going to influence those one of those three compartments, which is going to skew the results. So ultimately, there is lots of variability and measurement error, and you need to be aware of these sources of error so that as a technician, you try to minimize them by having controls in place. Now let's talk about another indirect method of assessment, and this is called air or water displacement. It can either be in the water, you can see the chamber that the individual is sitting in, and they be submerged in the water, and then you're supposed to exhale all of your air out of your lungs. And at that point, your weight is measured, and that's known as your body density, your mass over the volume. I remember doing this when I was an undergrad student at the University of Toronto. We went to the U of T indoor swimming pool, and we had this system where I remember sitting in that chamber, going underneath the water and trying to exhale every ounce of air out of my lungs. And then they do this measurement, which is pretty cool. So if you get a chance to do these, take advantage of it. And then the other one is air displacement, which is known as the bod pod. So you sit in this, it looks like a little space capsule. And again, you just sit there in minimal clothing with a cap on your head, because the influence of your hair can skew the ability of the air to displace your body mass. Okay, so you need to ensure that you wear a little cap and you're in minimal clothing, ideally spandex for the lower half, and obviously a sports bra as well. Okay, so this estimates body composition from determining body density. So we're using a surrogate parameter. In this case, it's body density. Once we have, so body density is determined by knowing the person's mass divided by their volume. So the mass is measured on a scale on land, and the volume is measured by air or water displacement in the bod pod chamber or underwater weighing. And the model partitions the body into only two compartments of constant densities. So it assumes that your fat mass and your fat-free mass have constant densities across all compartments of your body. So it's relatively, if you think about it, it's very simplistic. We're splitting your body into two compartments. Okay, fat mass and fat-free mass. So where does organ mass lie? Where does water content? All of this stuff has to be in one of those two compartments. This method also assumes that the relative amounts of fat-free mass components, the water, protein, bone mass, and non-bone mass, are fixed. And it also assumes that the more dense a body is, the lower the percentage of body fat. And the less dense a body is, the higher the body fat. And this is very influenced by the water content within your body. So if you arrive hydrated versus dehydrated, you could skew the results by upwards of 10%, which is pretty ridiculous. So this is why you need to control, as a practitioner, if you're going to be testing individuals with this method, you need to control their hydration beforehand. So the limitations to air or water displacement is it's inappropriate for individuals who deviate from the fixed and or assumed values. For children, elderly, obese, extremely lean, it's not as accurate because the regression equations that are inputted into the system are for normal, recreationally active, normal weight individuals. So this would not provide an accurate measure. So just be mindful of that. As well, a limitation is clothing. You want to ensure that you have the same amount or the same clothing on each test. So as you can see for Bod Pod, it's minimal garments. So it's a hat on, it's a spandex lower half of your body, and any undergarments need to be spandex to minimize the disruption of the air flow within the chamber. The same goes for hydrostatic weighing. This is also doubly indirect. So you're getting body density, and then you're using body density, putting that into a linear regression equation to determine fat mass and fat-free mass. As well, another limitation is it is lab-based. You need to have both hydrostatic weighing potential and air displacement potential, a Bod Pod. And then, as I mentioned before, hydration does significantly impact the results because we're not measuring total body water. Instead, total body water is quantified as either fat mass or fat-free mass. The next indirect method of assessing body composition, which you're probably most familiar with from the lab experience, is surface anthropometry. So this picture is a picture of skin calipers, which are calibrated to be able to look at the thickness of certain girths. So essentially, it measures the thickness of fat immediately below the skin surface. So we can either assess 3 sites or upwards to 12 sites. And its local fat measurements are used to predict the overall fat content of the entire body. So let's just think about this, that you measure 3 girths, 3 sites of an individual, the thickness of their fat, and assume from the thickness of that 3 sites what the body fat is for their entire body. To me, that seems extremely inaccurate. So to make it the most accurate, you increase the number of local fat measurements. So 12 measurements would be considered the most valid indication of what the overall percent body fat would be for your clientele. So the higher number of local fat measurements you're taking, the better or the more accurate of a predictor it would be of what the overall percent body fat of the entire body would be. So once the fat folds are measured, they are put into one of hundreds of different population-specific or generalized equations to determine percent body fat. So again, you want to pick a regression equation that's specific to your client. So their age, their demographic, their sex, their body mass, all of their activity level. It's very important. Otherwise, you will skew your results. So the accuracy of skin folds on an individual basis is not very high, with research studies indicating errors up to plus or minus 8%. So if someone is really 20% body fat, skin calipers could measure that person between 12 and 28% fat. So this has huge variance. So the best application is to determine if subcutaneous fat is increasing or decreasing over time, not for predicting total body fat. That I can't reiterate that enough, that it's so important. Surface anthropometry has a high source of error. There's high variance, and this depends on the technician, expertise, all of this stuff. And so the best method for surface anthro is to track changes over time, track changes in those individual skin caliper or local fat measurements, and you're tracking that over time, not on predicting total body fat. This is an example of a reliable method, but not valid assessment tool. It's not used for diagnosis, but it's used for serial tracking of change over time. Okay, that's very important. This is an example of a reliable, it will always give you a number, but not necessarily a valid assessment tool. Not used for diagnosis, but for serial tracking of change over time. Now let's discuss the limitations and benefits to surface anthropometry. First off, the limitations. There are assumptions made about the disposition of adipose tissue, such that the disposition underneath the skin at the site at which you're doing the skin caliper is indicative of the total body adiposity for that individual, which isn't quite correct. That just because you have fat mass in that area doesn't mean that the whole body has a higher amount of fat. Okay, so you have to be mindful of that. As well, the precision is highly variable and technician dependent. So how you assess someone may be different than how I assess someone. So you want to ensure that you have the same tester each time and they have their known measurement of error. As well, obese individuals, there are limitations to doing surface anthropometry on these individuals just for the difficulty of the skin caliper. As well, there are representative estimates of the total subcutaneous fat in the body. So you're estimating based on subcutaneous fat what the total adiposity is for that individual. So that's a limitation. The benefit is that it's convenient, it's cheap. A set of skin calipers can be anywhere between $100 to $300, and it's a cheap field-based measurement to easily track changes over time. The benefit is if you have determined your error of measurement, and as such, you can apply this to your findings to determine whether it's a true change or just based on chance. Now I'd like to discuss with you a comparison study that I did almost 7 years ago at the Canadian Sport Institute. So we have athletes who come in and get a DEXA scan, and then they go back to their daily training environment, and periodically they get skin fold assessments or surface anthropometry, and or they get a bod pod done. Well, as we know, each of these techniques are extremely different, and they all report percent body fat and lean mass differently. And so it's very hard to compare the results of each of these three types of measurement. So this study, what we wanted to do was compare field versus laboratory-based assessment comparisons. So we recruited 38 active individuals who exercised at least 4 times a week. They each did a DEXA, they each did a bod pod, and they each had surface anthro done at 10 sites. We also did girths and segmental volumes. What we saw was that there was a significant difference between the 3 assessment tools as we predicted. And this led to the development of a regression equation for which if someone is tested with the DEXA, you put in those values into a regression equation and it will predict what the score would be on surface anthropometry or bod pod. This slide showcases the results from the study. So we have the 2 different sexes, we have females and males, and then the combined results. What I want to draw your attention to is the difference between the means over on the right-hand side. So we see the difference between DEXA and bod pod for females was 2%. The difference between DEXA and skin fold for the females was 7.2%. So that's how much variance there was. So we'd have a DEXA value, say of 20% body fat, while skin folds will report that individual as being 12% or 27%. Okay, the difference between bod pod and skin folds for the females was 5.2% difference. For males, it was 3, 7, and 4 respectively. And then the combined differences between the measurement assessment tools. For DEXA and BOD-POD, it was 2.5%. For DEXA and SkinFold, it was 7.1%. And for BOD-POD and SkinFold, it was 4.6% difference. So what does this mean? What information can we glean from this study? Well, essentially, there was the greatest difference in percent body fat between the DEXA and the SkinFolds. That was the greatest variance between the two. Okay, the SkinFolds was less than the BOD-POD percent body fat, which was less than the DEXA percent body fat. So the DEXA, being the 3-compartment method, always reported percent body fat significantly higher than BOD-POD and significantly higher than the SkinFolds. So when we assess via SkinFolds, the result will be significantly less, around 7% difference between that and DEXA. Well, why is this? Well, the DEXA is a 3-compartment model. It is a little bit more accurate. It also doesn't make assumptions like skin calipers does, where we're just assuming whole body adiposity from determining 7 to 10 skin fold sites, which is subcutaneous fat. So from the results of the study, we are able to generate a prediction equation, which has a 95% confidence interval. So we showed that there's evidence of a linear relationship between percent body fat measured by DEXA and SkinFold. That essentially we had an R-squared coefficient of determination of 88%, or 0.88. So 88% of the variation in percent body fat calculated from DEXA can be predicted using this equation. And you can see it here. It's y equals 1.126 times whatever the x value would be from either the percent body fat you get from DEXA or from SkinFolds, plus the constant being 5.172. So we can predict percent body fat value from DEXA using SkinFold with 88% accuracy. One very important piece to ensure that testing is valid and reliable is the incorporation of testing standardizations. When it comes to research, we are very nitpicky when it comes down to testing standards, and this transcends all types of vocations. So whatever you go into after you graduate from this university, I highly recommend that if you are doing testing, that you incorporate and analyze the type of standards you have in place to ensure you're getting valid and reliable data. The first testing standardization for body composition assessments is being fasted. So this means 12 hours of fasting from hydration and food with avoided bladder. So the easiest way to control for this is do testing in the morning after the individual had 12-hour fast. So they come right into the lab, you get them tested right away on an empty stomach. So then you don't have food in the intestinal tract being quantified as soft tissue, skewing the results, and you don't have a huge amount of water in the system to influence total body water, which gets quantified in indirect methods as soft tissue. So in that case, it leads to the second one, which is the time of day. Ensure that you always test at the same time of day. Okay, this is important for serial tracking. If you're testing the same person over and over and over again, ensure you test them at the same time of day. As well, have a resting state, so no exercise in the past 12 to 24 hours, because this does impact fluid shifts and fluid dynamics within the body. As well, control for clothing. Ensure that they're always tested in the same minimal clothing. Have a pregnancy test for female athletes getting a DEXA scan. Ensure that you have the same technician and equipment used. This is extremely important because there is intra-tester variability, and there's lots of variance between equipment as we showcased in the previous slides. As well, you need a skilled and qualified technician to be able to run the tests and interpret them. And you must also calculate the machine and technician specific technical error of measurement. So the percent coefficient of variation and the least significant change, which I'll talk about on the next slide. And then lastly is providing an informed consent. Your client needs to know exactly what they're getting into, the risks and the benefits of getting this testing done, and they need to provide verbal and written consent to take part in this. These testing standardizations have been published by Nana et al. In 2014, and act as the gold standard and the current best reference method for determining body composition. So one major concern when it comes down to body composition and or any testing is the interpretation of the results, the interpretation of the data. Are the results a true biological change, or is it based on technical error? So if I fluctuate in my body composition from 5% body fat from 1 week to the next, is that an actual biological change, or is that based on just technical error, that there was errors in the way that it was tested? We need to know this. And so it is extremely important that the technician determines their precision error, also known as their least significant change or technical error of the mean. We all make flaws and we all have errors between measurements. So what does this mean? How will we determine our technical error of the mean? Well, this is what I do, and it's currently published, and this is the way in which you determine your precision error. So for example, if I was doing a DEXA scan, I would test 10 athletes 3 times or 15 athletes 2 times with repositioning in between. So what does this mean? Okay, so you decide to participate in this. I set you up on the DEXA scan. I scan you once. Okay, I get that data. I then take you off the DEXA and say, go back on the DEXA. I reposition you the best I can, similar to the previous position, and I scan you again. Now, there's going to be differences between those 2 scans, even though nothing within your biology has changed. It's more technical error. Okay, so the difference between those 2 scans may be 2%. So that means my technical error might be 2%. So when you're interpreting data from 1 week to the next, and the difference is less than 2%, and my technical error is 2%, I could say that that is not a biological change. If their result is less than 2%, that's an indication of technical error. Okay? Very, very important when it comes down to interpreting data. Is it a true change, or is it just technical error? So by doing this testing, you determine your coefficient of variation, your technical error of the mean. And that needs to be applied to the results and interpreted correctly. Okay, this is essential for proper interpretation of the results. Is it biological change or technical error? For example, Josh has a percent body fat precision error of 3%. His client, Mary, improves her body fat percent by 2.3%. Is this a true change? The answer should be no, it's not a true change, because it's within Josh's 3% error. That Mary is reporting a 2.3% change in body fat, but Josh's precision error between test to test retest is 3%, and this lies in that range, and therefore her change is not a biological change. Instead, it is technical error. Okay, this is a huge beef I have when it comes down to any testing. So even when you're doing VO2 max testing, there is error. If you tested an individual at 10 a.m. and tested that same individual again at lunchtime, you might get completely different results. And it could be about how the mouthpiece is positioned. It could be how the individual's effort is. All of these factors which impact the data. And so you need to know what the technical error of the mean is in order to interpret the data appropriately. So instead of telling Mary, yes, you improved by 2.3%, you dropped your percent body fat by 2.3%, and she's so excited, but this wasn't actually a biological change. This could be just technical error in the results. So it's very important that you determine your technical error of the mean through this method of testing 10 athletes 3 times or 15 athletes twice with repositioning in between. So there are some accreditations that you can pursue if body composition is something that you forecast as being a tool that you're going to use in your toolbox when assessing clients. There's 2 accreditations that I recommend. One is through the International Society for the Advancement of Kin Anthropometry, also known as ISAK, and this is for surface anthropometry. And through this program, there's a level 1, level 2, and I think a level 3 technician. You're able to increase your ability to do surface anthropometry. Within that accreditation, you have to determine your precision error so that you know that, so that when you have a client, you can tell them with confidence that this was a biological change and not just due to my own technical error. So that's one, it's the ISAC. The second one is if you want to start working with DEXA, or the workplace that you're going to be starting at has a DEXA and you want to get trained on it, there's a society called International Society of Clinical Densitometry, where there's a technical course and or a clinical densitometrist course where you have to be an MD or PhD to do that route. But those are the two accreditations that you can consider if this is something you would like to pursue. So just to recall, the point of assessing body composition is to assist in tracking progress towards the goal. So depending on the needs analysis and the gap analysis of your client, if body composition is a tool you would like to integrate into the training program to track progress towards health or fitness or performance related goals, then incorporate it. Just ensure that you have specific goals in place and checkpoints that you want to try to aim to hit with proper exercise and or nutritional interventions. So in summary, each method of body composition has inherent flaws. So you need to pick one and stick with it. Okay, so you need to pick, if you're constantly doing surface anthro, that's what you choose. You're going to stick with it. You're going to determine your precision error and you're going to use it, that same calipers, with your client over and over and over again in serial tracking to monitor their progress. So pick a method and stick to it, because each of them, as we presented today, have inherent flaws. So it comes down to validity versus reliability. Okay, and sometimes you just want a reliable method, and validity comes with time. As well, you want to ensure that you have a skilled technician with proper training to maximize precision and decrease intra and inter-rater variability. You want to ensure that the technician that you use is consistent, that you always use the same technician and equipment. And the most important piece is you determine the precision error. What is your technical error of the mean, your TEM? And apply this to the findings to be able to report whether it was a true biological change or just due to technical error. Okay, so practitioners should be aware that even with the use of technologically sophisticated methods like the BOD-POD or DEXA, differences between methods exist, and the determination of body composition is at best an estimation. So it's not necessarily the most valid approach, but it's reliable. So pick one method and stick to it. So in summary, from the entire course, the course theme is really understanding the underpinning physiological responses and adaptations for specific program design and performance outcomes. So it all comes down to having a proper needs analysis. That's so important, which dictates the types of assessments you'll do, which drives your gap analysis, which dictates your specificity of exercise prescription. So the specificity of exercise prescription, it's all about picking the most appropriate method of assessment for your client based on their needs and their gaps. And that specificity of exercise prescription drives the physiological change, whether it be the rate of force development, the stretch reflex, the shortening cycle, motor unit recruitment, muscle fiber changes. All of these are a function of your exercise prescription. Those physiological changes result in performance outcomes that we assess performance outcomes. We assess agility, we assess speed, we assess endurance, we assess anaerobic capacity. And then from there, once we start to see the performance outcome as a result of our exercise prescription and adaptations, we monitor. We monitor load, we monitor freshness and fatigue, we can monitor body composition and tie that into performance outcomes. And all these factors help us to prescribe appropriately and reinforces our program that it's being effective. So prescription is dictated by the needs, your goals, the gap analysis, the experience, the time you have with your client. You really want to follow that FIT principle, frequency, intensity, type, and time, and load parameters, plus freshness and fatigue monitoring strategies. So I hope you enjoyed this course. I had a pleasure. It was all my pleasure to teach you and instruct you. Please reach out to me with any questions you may have. And I wish you the best for your forthcoming vocation. Please, again, reach out to me with any further questions. Thank you.